The James Webb Space Telescope has just captured a mysterious six-pointed star hovering right above the giant hexagon at Saturn's North Pole. In the infrared glow, that polar region appears with its colossal hexagon and a bent six-pointed star suspended above it, while far below Earth is breathing slowly held together by plate tectonics, the carbonate-silicate cycle, and a thin atmosphere just stable enough for fire and technology to exist. Around us, a sphere 33,000 light-years across may be completely silent. Any civilizations that do exist could be flickering out of phase with us, like brief sparks, and the dream of launching billions of self-replicating probes still lives only on paper. On top of that canvas lie impact scenarios and ancient scars 2024. YR4 might one day strike the moon, triggering a brilliant but dangerous storm of micrometeoroids, while Mercury stands as a stripped world little more than an exposed iron core. In contrast, we are trying to plant life beyond Earth tea gardens grown in lunar regolith simulant undernourished lettuce on the ISS, and crops that may need genetic modification to survive inside glowing greenhouses on other worlds. Farther away, the light of a distant galaxy is bent into an Einstein cross, with a mysterious fifth point that only appears in our models when dark matter is added. And back on Earth, NASA sometimes has to halt website updates due to funding issues, yet its control rooms remain lit quietly, protecting the ISS preparing Artemis II and maintaining the fragile thread that ties humanity to space. Do these new findings from James Webb have the power to rewrite the cosmic history we believe in? That journey of discovery continues right after this. Beneath the haze of Saturn's upper clouds, the North Pole glows in a faint blue light. The planet turns slowly like a memory suspended in time. Yet from that soft motion rises something impossible, a perfect hexagon vast enough to hold our entire world within its borders. Astronomers first saw it through Cassini's unblinking eye, a storm that refused to spiral like every other vortex in nature. 6 sides precise as geometry, drawn by an invisible hand. Some wondered if the shape was deliberate a sign of order imposed from beyond. Others whispered that it was simply air and temperature playing their ancient game. Science offers a calm reply when jet streams race around a pole at different speeds. Standing waves can form eddies that twist the wind into repeating shapes. In a laboratory, liquid in a spinning tank has recreated the same structure. Hexagons, octagons, even circles that collapse into corners. The universe, it seems, carries rhythm in every scale from molecules to storms. But there's a gentler mystery here. Saturn's hexagon has lasted for decades, maybe centuries undisturbed, while storms on Jupiter come and go. Its walls rise higher than Mount Everest, and each side stretches 20,000 kilometers long. Imagine clouds flowing through it, glowing faintly gold beneath sunlight scattered by ammonia ice. It breathes, expands, contracts, like a living lattice over an alien sea of gas. If you were drifting above it now, you might see the edges pulse in slow motion, as if the planet were tracing a symbol for anyone patient enough to notice. A symbol of repetition and balance. Or perhaps a reminder that even chaos has form. And still the question lingers in the quiet air between thought and sleep. Who designed the hexagon of Saturn? A storm, a pattern of physics, or something older that simply learned how to hide within the laws? We think we understand. High above the hexagon's steady breath, Saturn's atmosphere thins into an amber haze. There in the infrared glow captured by the James Webb Space Telescope, something faint begins to shimmer an outline no human eye has seen directly. 10 hours of patient observation reveal a crooked star, 6 arms bent slightly, as if the wind itself had tried to draw a symbol and wavered halfway through. 4 of those arms match perfectly with the vertices of the hexagon below, connecting storm to stratosphere like invisible gears in a vast machine. The other 2 fade into nothingness, as though the pattern were half hidden by another layer of cloud or by a rule of physics we haven't written down yet. In that thin region, 500 kilometers above the main cloud tops, hydrogen ions dance under Saturn's magnetic field, their faint light forming the arcs Webb recorded. Scientists suggest it may be a resonance between atmospheric waves and the planet's magnetosphere, a coupling so delicate that even slight shifts in temperature could twist the figure's symmetry. Others imagine it as a mirage of data, a trick born of changing altitude and radiation, no more mystical than sunlight on rippled water. Yet when the image plays in slow motion, the 6-armed star seems alive, its limbs breathing, curving, touching the edges of the lopsided hexagon below. It is both motion and stillness, chaos and order, a reminder that geometry is not always silent. Perhaps it is only a ripple of energy passing through cold hydrogen. Or perhaps it is the planet's quiet attempt to speak a language written in wind for anyone still awake enough to listen. Far below the six-armed star, the polar hexagon keeps turning patient and unwavering. Between Chung and other shape waits in the middle layers of Saturn's air, a faint secondary hexagon reported in 2018, around 300 kilometers above the clouds. One at the cloud tops, one in the middle atmosphere, and now a crooked star in the thin air above them both. 3 levels, 3 patterns, 1 planet. The gentlest explanation is also the most conservative layers of wind stacked on top of each other like different currents in an ocean. Each layer carries its own waves, its own jet streams, its own rhythm. When those rhythms line up, they can carve repeating structures into the gas hexagons, arcs, dark patches in the aurora, a purely natural choir of air and magnetism. Another hypothesis suggests a vertical resonance column, where energy from the deep atmosphere travels upward, guided by Saturn's rotation and magnetic field. In that picture, the lower hexagon, the middle hexagon, and the bent star are simply different verses of the same song, each sung at a different height. Beautiful, but still within the laws we know. And then there is the quiet thought we rarely write into papers that some patterns feel too deliberate, even when they are not. Our minds are tuned to see symbols to search for messages in clouds and constellations. Maybe Saturn is not sending a signal at all. Maybe it is only being itself. Yet as you imagine those stacked shapes slowly drifting around the pole, it is hard not to feel that the planet is tracing something meaningful into the dark, an ancient handwriting in wind that we are only just learning to read. From space, Earth looks almost asleep, a dim blue ember breathing beneath soft white veils. Clouds drift like thought. Continents slide so slowly that even the memory of mountains fades before they move. If you wait long enough, the whole planet seems to inhale and exhale. The oceans rise, the crust sinks, the air thickens, then thins. It is rhythm, not motion, an ancient planetary pulse. To scientists, this rhythm has a nameplate: tectonics. Beneath every forest and desert, slabs of rock glide over a layer of molten stone, colliding, splitting, diving into the mantle. Each movement recycles carbon, traps water, and exhales volcanic breath back to the surface. The process is so slow that no human lifetime can feel it yet without it. The atmosphere would choke or freeze. It is the hidden heartbeat that keeps the climate steady enough for rivers, for lungs for us. Sometimes we imagine Earth as silent stone, but in truth, it murmurs constantly in earthquakes too deep to hear, in magma veins that surge like blood. Every continent drifts a few centimeters each year, rearranging the map with a patience no civilization could match. The planet isn't alive in the way we are yet. It behaves as if it dreams. Each breath, each tremor, each storm is part of its long conversation with the sun. If another civilization were watching from across the stars, they might see our world not as a rock, but as a living pulse of blue and white exhaling clouds inhaling light. Perhaps they would give it a name that means the planet that breathes slowly. And tonight, as we drift with it, our own breathing falls into the same rhythm, steady, ancient, shared. Deep beneath the quiet oceans, a slow exchange is always underway. Rain falls through air that contains carbon dioxide, becomes slightly acidic, and seeps into cracks in the continental crust. It dissolves silicate minerals grain by grain, carrying ions down rivers to the sea. There, over long ages, they settle as carbonates on the ocean floor, thin patient pages in a stone archive of the atmosphere. This is the carbonate-silicate cycle, Earth's long-term breathing system for CO2. Plate tectonics turns its pages. As oceanic crust moves away from mid-ocean ridges, it cools, grows dense, and eventually dives back into the mantle, at subduction zones, dragging those carbonates with it. Deep below, heat and pressure break them apart, releasing carbon dioxide into rising magma. When volcanoes erupt, that buried gas returns to the sky, closing a loop that can take tens of millions of years to complete. If the planet grows colder, chemical weathering slows, less CO2 is removed, and volcanic outgassing gently raises greenhouse levels again. If it warms, weathering speeds up, drawing more CO2 out of the air and easing the temperature back down. Over geological time, this cycle acts like a thermostat, keeping liquid water stable on the surface despite a brightening sun. To us it's invisible, no ticking clock, no needle on a dial. Just rain, rock, river, and fire balancing each other on timescales far beyond memory. Yet every calm night, every stable season quietly depends on that deep, unhurried negotiation between stone and air. Earth's air feels endless from the ground, but from orbit it is a thin blue line, a fragile film clinging to stone. Within that narrow band, the balance of gases decides whether a spark becomes a flame, and whether a flame can become technology. Our atmosphere holds about 21% oxygen. Drop that below, roughly 18%, and fire struggles. Wood smoulders instead of burning clean. Flames starve and die. Without easy fire, metals stay locked in ore. Ovens never reach the temperatures needed to smelt copper, iron, steel. No forges, no engines, no rockets, no telescopes to notice Saturn's hexagon at all. A small shift in chemistry and the path from campfire to spacecraft might close before it ever begins. At the same time, too much oxygen would turn forests into tinder, a world where lightning writes in wildfires. The narrow middle band is where controlled flame can exist, dangerous but teachable. Our planet has wandered over hundreds of millions of years through different atmospheric states. Yet again and again, it has returned to this precarious zone where lungs can breathe and embers can catch. It is easy to imagine that such a window is common, that many worlds hover near the same edge. It is just as easy to imagine that it is rare. Tonight, as your own breath slips in and out of that shared invisible ocean, you are part of the same delicate equation. One more small flame living for a while inside a very narrow band of air. Imagine drawing a circle around the sun not in kilometers, but in light years. 10 light years, 100, 1,000. You keep expanding until the radius reaches 33,000 light years, slicing through arms of the Milky Way like a quiet ripple through a spiral of stars. Within that volume lie hundreds of billions of suns, each with its own retinue of planets, moons, and frozen comets. Now imagine that in all that space not a single other civilization with radio dishes and rockets is active at the same time as we are. No other cities spilling light into night, no other species sending out signals, no one else looking back at us. Just us in a bubble of potential silence, 33,000 light-years wide. That is the picture. Some versions of the rare Earth calculations suggest not proof, but a stark possibility. Our own technological shout into the galaxy has barely begun. Radio and television waves have travelled outward for little more than a century, forming a sphere only about 100 light-years across. Compared to the 33,000 light-year radius of that hypothetical solitude, it is a tiny ember glowing in a vast, dark hall. Most of the stars inside that hall have not even been touched by our faint whisper yet. If no one answers, it may be because no one is there. Or it may be because anyone who could answer is too far away for their reply to return before our species is gone, our instruments dismantled, our languages forgotten. There is a strange comfort in this too. In a galaxy that might be so quiet, every thought you have, every story we tell, every small act of curiosity becomes part of the only known conversation the universe is having with itself right now in this corner of space. The image of that 33,000 light-year bubble comes from more than imagination. It grows out of equations. Researchers take what we know about Earth and turn it into a long chain of filters. How often do stars like the Sun form? How many of them keep planets in a stable, gentle orbit for billions of years? Of those planets, how many have the right mass for an atmosphere, enough water, a protective magnetic field? Then the conditions narrow further. A large moon to steady the tilt. Plate tectonics to recycle carbon and keep temperatures in a livable range. An atmosphere that allows liquid water yet does not strip itself away or collapse into ice. After that, they ask for time, billions of years, without being sterilized by supernovae impacts or runaway greenhouse events. Each step is assigned a probability, sometimes measured, sometimes guessed. Multiply all those fractions together, and the number of truly Earth-like, long-lived, technologically capable worlds may shrink to something very small. In that framework, it is not surprising that the nearest neighbours might sit tens of thousands of light-years away. But inside those equations lies a quiet confession. Almost every parameter is tuned around a single example, our planet. We do not know how many different paths lead from chemistry to cells, from cells to minds, from minds to machines. We do not know whether life can flourish in oceans of methane in high-pressure clouds, or under ice thicker than any on Earth. The model assumes that other stories must rhyme with ours. Perhaps that is true, or perhaps our calculations are like a map drawn from one small island pretending to describe an entire ocean. The numbers are useful, but they are also a mirror reflecting how little we truly understand about the many ways a universe can become aware of itself. When we imagine other civilizations, we tend to place them beside us in time as if they were neighbours living just over the next hill. But the galaxy is not a village. It is a clock with many hands, each one sweeping across billions of years. Two worlds can be close in space and utterly misaligned in history. On one planet, life might have bloomed early, raced through microbes and multicellular forms, built cities under alien skies, and then faded away a billion years before Earth's continents even settled into their current shapes. Their last radio transmission, if they ever invented radio at all, could have crossed our orbit long before our atmosphere held enough oxygen for fire. On another world, the first complex cells may still be forming now deep under ice or in some warm, lightless sea. Their future telescopes will turn to the stars long after our species has gone quiet. In this view, civilizations are not scattered like lamps in a room, all burning at once, but like brief sparks along a wire flashing at different moments rarely overlapping. Even if the galaxy is full of minds, most may never share an era. So when we listen and hear only static, it may not mean we are alone. It may simply mean that for now our part of the universe is between sparks holding its breath between one flash of awareness and the next. Long before we ever left Earth, people dreamed of sending messengers instead of themselves. That dream became a question in physics. What if a civilization could launch self-replicating machines, tiny smart seeds that cross the galaxy on the currents of starlight? They are called von Neumann, probes, small craft that harvest raw material from asteroids, copy themselves and move on. In theory, a single probe could build billions of descendants filling the Milky Way in only a few million years. Mathematically, it's possible. Practically, it feels like myth. No telescope has ever caught a glint of one. No faint metallic echo has returned from interstellar dust. Still, the idea persists. Some suggest that ancient probes could hide among comets disguised as rock and ice asleep until they are noticed. Others think they would be too small to detect nanoscopic fleets drifting between stars, recording, waiting, perhaps already watching. If even one civilization began such a project eons ago, the galaxy should already be humming with their silent traffic. Yet we see nothing. Maybe the dream is the message itself. When we imagine these self-replicating seeds, we reveal what we wish for: continuity, a way to outlive the short pulse of our own spark, to build something that can keep asking questions after we fall silent. In that sense, the first von Neumann probe already exists. It is this idea travelling from mind to mind, carrying the urge to explore farther than our bodies ever can. In the catalogue of Near-Earth Asteroids 2024, YR4 is just a line of numbers, a small rock dark and cold circling the sun on a path that sometimes brushes the orbit of our world. It has no name, no myths attached to it, only coordinates and uncertainties. Yet for a brief moment it stepped into the spotlight of our attention. When its orbit was first calculated, the numbers allowed a narrow corridor, a 3% chance that years from now, this unremarkable stone might intersect Earth. 3% is small if you are rolling dice. It is not small if you're dealing with worlds. Telescopes turned computers refined the trajectory, and the probability for Earth slowly sank towards zero. The planet exhaled even if most of its inhabitants never knew they had been holding their breath. But the story didn't end there. As the models improved, a different possibility emerged around the year 2032. There is roughly a 4% chance that 2024 YR4 could strike the Moon instead. Not enough to be certain, more than enough to be taken seriously. A small impact on a dead, airless world, harmless perhaps, or perhaps not. A cloud of debris, a spike in micrometeoroids around Earth's orbit, a brief spectacular storm of artificial shooting stars, and a risk to satellites we depend on. So the question becomes larger than the rock itself. Do we let nature run its course, treating the impact as a free experiment in celestial mechanics? Or do we intervene, nudge the asteroid aside with a mission like DART, accepting the cost and responsibility of changing an orbit on purpose? Somewhere in the darkness, 2024 YR4 continues its quiet journey indifferent to our debates. It is we who must decide what kind of species we want to be when a small stone raises a very large question. If 2024 YR4 were to strike the Moon, the moment of impact would pass in silence for us. No sound crosses that gulf. Just a flash of light on a grey airless surface, a plume of dust and rock thrown high above the crater rim. But physics would not stop at the Moon. Ejector launched at several kilometers per second could escape its weak gravity, spreading into space as a cloud of tiny fragments, each one a future streak of fire. Models suggest that in the weeks or months after such a collision, the density of micrometeoroids near Earth's orbit could rise dramatically, hundreds, perhaps 1,000 times the usual background for a short interval. Most grains would be no larger than sand, but at orbital speeds they carry the energy of bullets. For satellites, space stations, and delicate solar panels, that is not poetry, it is risk. Engineers imagine shields flexing sensor readings, spiking alarms chiming in quiet control rooms, while the invisible rain passes by. For those on the night side of Earth, though, the sky might become astonishing. Storms of shooting stars could pour across the darkness, not as a gentle drizzle, but as a luminous river tens or hundreds of streaks each minute, tracing the paths of particles born from that single lunar impact. People might stand outside in fields and on balconies watching the heavens burn with borrowed dust, never knowing the exact calculations and anxious meetings that preceded the show. That is one of the strange balances our age inhabits. The same event that could give us the most beautiful meteor display in centuries might also threaten the quiet machinery that connects our world. Beauty and danger written in the same falling lines of light. And above it all, the moon would turn once more scarred in silence, as if nothing extraordinary had happened at all. Far closer to the sun than we are Mercury circles in a furnace of light. It is a small world, but strangely heavy. When spacecraft measured its density and gravity field, they found that Mercury is mostly metal, an oversized iron core wrapped in only a thin shell of rock. By mass, that core makes up nearly 70% of the planet. Compared to Earth with its thicker mantle and crust, Mercury looks like a world that has been stripped. For a long time, the leading idea was simple and violent in the early chaos of the solar system. A much larger body struck Mercury, blasting away most of its outer layers and leaving the core exposed. One colossal impact, one reshaped planet. But detailed simulations showed problems with that picture. The debris from such a collision often falls back or escapes entirely, or leaves behind a planet that does not match what we see. The story, it seems, is more complicated. Newer models suggest a different kind of ancient violence. Instead of one big projectile hitting a smaller target, two proto-Mercury's worlds of similar size may have collided head-on. In some scenarios, multiple impacts over time chip away at the lighter rock while denser iron sinks and coalesces. The result is a compact metal-rich planet forged not in a single blow, but in a series of crushing encounters. No one was there to watch. No eyes saw the molten horizons, the arcs of vaporized stone, the long rain of droplets cooling into a new world. Yet every time we map Mercury's gravity, we are reading the fossil of those collisions. It is a reminder that planets like people often carry deep scars from events they no longer remember, shaped quietly over eons by impacts that ended long ago. On the Moon, there is no breeze to rattle leaves, no rain to soak the soil, no air to carry the scent of anything green. Its ground is made of shattered glass and dust regolith ground, fine by billions of years of impacts, sharp-edged and utterly dry. And yet in a laboratory on Earth, under lamps that mimic distant sunlight, scientists have taken soil made to imitate that lunar dust and pressed a small seedling into it, a tea plant. The experiment is simple in appearance, a tray of grey grains, controlled light, measured water and nutrients, beside it for comparison ordinary earth soil or a neutral substrate. Under the same conditions, the roots explore both worlds. They wrap themselves around volcanic fragments slipped between dust particles that have never known a river. Slowly pale stems rise, leaves unfold. Against that artificial moon, a small patch of green appears impossibly soft on a landscape built to be hostile. What grows there is more than a plant. It is a question: how much of what life needs can we carry with us, and how much can we coax from alien ground? The lunar simulant is poor in organic matter, lacking the rich microbial life that feeds roots on Earth. So the scientists supplement, adjust, compensate. In doing so, they are rehearsing in miniature the choreography future settlers will need to keep their gardens alive under hard airless skies. Imagine one night a habitat buried under regolith for protection, outside a horizon of grey and black, inside a narrow room lit in warm gold rows of low shrubs breathing out faint moisture. Someone stands at a small window watching Earth hang above the lunar plain while steam curls from a cup, brewed with leaves grown from stone dust and patience. In that moment, the moon is no longer only a dead companion, it is a place that can hold a garden. Mars is less forgiving. Its soil simulant mixed on Earth from crushed basalt and salts looks similar to the lunar mix at a glance, another grey dry powder. But chemically it is harsher. Perchlorates and oxidizing compounds lurk within it, the ghosts of strange Martian chemistry. When scientists try to grow the same tea plants that survived in lunar-like soil, the seedlings struggle. Roots hesitate. Leaves yellow. Some never unfold at all. It is a quiet reminder that not all worlds are equally welcoming. The moon is barren but comparatively simple, rock and glass mostly inert. Mars carries a more complicated history in its dust, shaped by thin air, ancient water, and a constant drizzle of radiation. To turn that dust into farmland is not just a matter of adding water. It is an act of transformation, of cleaning and reshaping what the planet offers. Even in orbit, where conditions can be controlled down to the watt, and gram plants betray their discomfort. On the International Space Station, astronauts have grown lettuce under LEDs, coaxing leaves from pillows of nutrient substrate. The harvest looks fresh and bright, but analysis reveals the difference: calcium down by about 30%, magnesium by roughly 25% compared to Earth-grown leaves. In weightlessness fluids, drift roots experience a strange directionless environment, and the plant's inner logistics falter. So we face a simple but profound question. If we wish to live far from Earth, can we rely on unmodified life? Or will we need to reshape our crops through selective breeding, through genetics, to thrive in alien chemistry and weightlessness? Somewhere between these experiments and that question lies the outline of humanity's future dinners in space, salads grown above a blue planet or in domes under red and grey skies. To make gardens in space truly endure, we may have to change more than soil and light. We may have to change the plants themselves. On Earth, every leaf and root is the product of billions of years of evolution tuned to one set of conditions, one gravity, one mix of gases, one spectrum of sunlight filtered through one sky. Beyond that sky, the rules bend. Radiation is harsher. Day and night can be months long. Up and down become suggestions rather than laws. Genetic engineering offers a careful way of asking plants to meet those new rules halfway. Biologists imagine crops with thicker cell walls to withstand radiation, roots better at clinging to dry, stony substrates, and metabolisms that thrive on lower pressures and unusual nutrient balances. A lettuce that keeps its calcium in microgravity. A wheat that tolerates Martian perchlorates. A tea bush whose leaves still unfurl sweet and green under the cold hum of LEDs. None of this is guaranteed. Each modification brings trade-offs, and every ecosystem, no matter how small, has its own fragile equilibrium. A greenhouse on the Moon or Mars would be less a farm and more a tiny engineered climate where pumps, filters and circuits stand in for rivers and seasons. The plants inside would be collaborators in our survival, not decorations. Picture one of those greenhouses at the edge of darkness, a transparent dome half buried in regolith, its underside glowing softly against the black. Outside, the landscape is silent stone and long shadows. Inside, leaves rustle under fans, droplets bead on plastic, and roots tangle through trays of tailored soil. A sensor blinks, a nutrient line pulses, and somewhere a modified seed completes the quiet work it was redesigned to do. In ordinary life, light feels simple. You flip a switch, and it travels in straight lines across a room, casting sharp shadows on the wall. But in the deep fabric of space-time, light is more obedient to gravity than to our intuition. Where mass bends the grid of reality itself, light does not argue, it follows the curve. Einstein's theory of general relativity describes this. Gently matter tells space-time how to curve, and space-time tells light how to move. A massive object, a star, a galaxy, a cluster of galaxies does not just sit in space. It reshapes the lanes through which light can flow. When a distant source lies behind such a mass, its light may be deflected, split, or wrapped around like a river dividing around an island. From Earth or from telescopes in orbit, we sometimes see the result as a ring or an arc, a phenomenon called gravitational lensing. A single galaxy might appear as multiple images arranged in a curve. An entire background of faint galaxies can be stretched into delicate streaks, as if the cosmos were being viewed through a glass sphere. These patterns are not illusions. They are maps of the invisible curves drawn by gravity. To a sleepy mind, there is something comforting in this. Light is still moving in straight lines, but those lines are straight within a space that itself is curved. The universe keeps its rules. It is our perspective that must bend. When you look up and imagine photons crossing billions of years, quietly adjusting their paths around unseen wells of mass, it is easy to feel that every star you see has taken the long, thoughtful way to reach your eyes. Far across the universe, a small group of foreground galaxies sits between us, and a much more distant one, something like 4 lanterns hanging in front of a far-off city. In visible light, they seem ordinary enough elliptical smudges of old stars bound together by gravity. But when astronomers pointed powerful telescopes toward them, they noticed a strange pattern nearby, 4 tiny points of light arranged in a rough cross around the group's centre. Each had the same spectrum, the same redshift, the same fingerprint. All 4 were not different objects, but 4 images of a single background galaxy, whose light had been bent into a shape called an Einstein cross. That much, while beautiful, fits comfortably inside the theory. A mass in front, a source behind, and space-time curved into a lens that splits the light into multiple paths. What unsettled expectations was the extra point. Nestled closer to the middle of the foreground group, there appeared a 5th fainter image of the same distant galaxy again, with matching spectral lines again at the same immense redshift of around 3. It was as if the mirror had produced one more reflection than it should. Astronomers ran their usual models, feeding in the masses and positions of the 4 main lensing galaxies. In simulation, the light from the background source arced and divided, but the predicted images never quite matched what the telescope saw. 4 points were easy. 5 were stubborn. The central image in particular refused to appear with the right brightness and location, unless something unseen was added to the calculation. On the sky, the pattern looks almost delicate, a cross with a dim ember in its heart. Yet in that extra point lies a quiet challenge. If gravity has drawn this figure with such precision, then the mass doing the drawing may not be limited to the stars and gas we can see. When the simulations refused to cooperate, the astronomers did what scientists often do in quiet crisis. They began to add what was missing. First, they tweaked the visible masses, adjusting the stars in each galaxy, the gas between them, the shapes of their halos. The light rays in the computer bent and split, but the pattern still came out wrong. The 4 outer images of the distant galaxy could be reproduced more or less, yet the faint central point stubbornly refused to appear where the telescope said it should be. The next step was to include what cannot be seen directly: dark matter. Instead of treating the lensing group as just 4 bright islands of stars, the model wrapped them in a larger, smoother halo of invisible mass. This dark envelope deepened the gravitational well, subtly reshaping the contours along which light could travel. When the researchers let photons trace paths through this new landscape, curved not only by visible matter, but by an unseen scaffold, the picture changed. Now the 5 images emerged in the right places with the right relative brightness. The stubborn central ember appeared no longer an outlier, but a natural consequence of the deeper potential well. The model did not prove dark matter exists, but it behaved like a key. Turn it one way, and the door of the Einstein cross remained closed. Turn it the other, and the pattern opened cleanly into view. There is something quietly humbling in that. Most of the mass shaping this scene is invisible, detectable only through the way it bends light and guides orbits. We are mapping a structure we cannot touch by watching how distant galaxies are rearranged into crosses and arcs. In a universe where so much is dark, sometimes the surest evidence of what is there comes from the shapes of what is not. Telescopes will return to this peculiar cross again and again. With sharper images and deeper exposures, astronomers will look for subtle signatures that the models predict: faint streams of gas between the lensing galaxies, tiny distortions in nearby background objects, delicate arcs too dim to have been noticed before. Each new observation is a way of tapping the glass, listening for the echo of the mass behind it. If the pattern of 5 images continues to match models that include a dark halo, confidence will grow that unseen matter truly sculpts the scene. If instead discrepancies remain, brightness, mismatches, extra distortions, missing arcs, then more radical possibilities may creep in. Perhaps gravity itself behaves differently on these scales. Perhaps our equations, elegant as they are, still lack a term. For now, the Einstein cross with its 5th point is like a question mark pinned to the sky. Long after you fall asleep, light from that distant galaxy will keep curving through invisible wells, tracing the same paths over and over. Our understanding may change. The pattern will not. It will wait patient and silent until we are ready to read more of what it has written. On some evenings, astronomers and students and curious night owls type a familiar address into their browsers, NASA's website, a doorway to missions and images and data that pull the mind upward. On most nights, the page blooms with nebulae and launch schedules, updates from Mars, plans for the Moon. But on certain rare days in recent history, the screen has opened to something else entirely, a quiet bureaucratic sentence. Due to the lapse in government funding, this website is not being updated. Behind that dry line lies a sudden stillness when the US government enters a funding shutdown. Agencies like NASA must send most of their people home. Of roughly 18,000 civil servants, about 15,000 can be placed on unpaid leave. Projects pause, emails go unanswered, offices that usually hum with work sit dim, their whiteboards frozen mid-equation. The universe does not notice, but for a little while our organised curiosity blinks. From the outside, nothing in the sky changes. The International Space Station continues its 90-minute circuits. Satellites still pass overhead in silent arcs. The sun flares and calms, indifferent to our budgets. Yet on the ground, teams that would be processing new images or planning future manoeuvres are told to wait. Observations scheduled months in advance may slip. Proposals sit in digital inboxes untouched. There is something unsettling and oddly human about this contrast. A cosmos in constant motion, and a space agency on pause because of arguments over numbers on paper. For a brief time, the front door of NASA becomes a sign that says, in essence, we're closed for now. Still, even in that pause, some lights remain on. Essential missions cannot sleep. And somewhere inside those quiet buildings, a few control rooms stay awake, watching the sky for all of us. Even when budgets stall and offices empty, some rooms inside NASA and its partners never go dark. In those spaces, the night shift slips into their chairs, headsets click on, and rows of screens bloom with data from hundreds of miles above Earth. Orbital mechanics doesn't pause for politics. Neither does the need to keep people safe in space. The International Space Station circles the planet roughly 16 times a day, a compact habitat moving at more than 7 kilometers per second. Its orbit must be monitored, its attitude adjusted, its life support systems checked and checked again. Flight controllers watch pressure readings, oxygen levels, the slow drift of CO2 scrubbers. They track fragments of debris, calculating whether a cloud of old paint chips or a broken satellite might cross the station's path. If the numbers line up the wrong way, they plan a maneuver, turning equations into a gentle push that keeps the crew clear. Other consoles follow robotic explorers and telescopes, making sure that antennas stay aligned, batteries stay warm, and instruments wake and sleep on schedule. In a shutdown, the list of what can be tended shrinks to only what is critical: human lives, high-risk assets, machines that cannot be safely left alone. The people who remain take on a strange kind of duty, knowing that much of the agency has fallen silent while they continue to watch the sky. Outside their windows, most of the world is unaware. City lights burn, clouds drift, planes cross the dark. But inside these control rooms, illuminated by monitors and status LEDs, humanity's connection to space is held in a steady, careful grip. Even when the homepage says close the line between Earth and orbit stays unbroken. Artemis Desu lives on the timeline as a set of dates and milestones. But beneath those numbers is a simpler picture. 4 humans in a small spacecraft looping once around the Moon and coming home. It will be the first crewed journey beyond low Earth orbit in more than half a century, a sequel to Apollo, written with new hardware, new politics, and new expectations. Manuals are drafted, simulators, tuned checklists rehearsed until they become almost like prayers murmured to machinery. Government shutdowns do not cancel a mission like that, but they do breathe uncertainty into its schedule. Training can continue, critical engineering can move forward, yet every pause in paperwork, every delay in testing or reviews, stretches the timeline in ways that are hard to see day by day. Launch windows move, no earlier than slips from one month to the next. A journey measured in hundreds of thousands of kilometers starts to feel vulnerable to arguments measured in budget lines and election cycles. Artemis Therp is more than a flight plan. It is part of a quiet race to return humans to the vicinity of the Moon before others do, to prove that deep space is still within reach, to rekindle a sense that the sky is not a finished story. When funding falters, the mission does not vanish, but it learns to live with fragility. Engineers design with contingencies. Astronauts train knowing that the dates circled on calendars may change, while the trajectory around the Moon remains the same geometry, waiting patiently in the language of orbits. From a distance, there is a kind of humility in that contrast. Our schedules are temporary, our debates loud and brief. The path around the Moon that Artemis II will follow whenever it flies has been there for billions of years, an invisible curve in space indifferent to whether we ever choose to trace it.